Hello, Riles. A little bit of extra work for lesson 2.3. I want to show you the algebraic approaches to the inequalities that we solved graphically in class to try to convince you. I mean, I said in the lesson that it is strongly recommended that you work graphically. I want to show you it is possible to do it algebraically, but hopefully if you're thinking about trying it that way, this will convince you that it's not a great idea. I'm going to start with the second of the two algebraic examples. It is not as bad as the first, so we'll sort of work our way up to it, kind of thing. The question said, given h of x equals 3x minus 2 all squared plus 5, determine the domain of this function if we restrict the range such that h of x is greater than or equal to 32. Setting the function equal to 32 and then solving by factoring seemed to be pretty easy. We draw the sketch, we read it off the sketch, no problem. If we wanted to do it algebraically, what we could do is we could set this right here is h of x. I want h of x to be greater than 32. That is h of x. So replace h of x with 3 times x minus 2 all squared plus 5 and say that that has to be greater than 32. Actually, even getting this far is a bit of a challenge for some students. They're not sure what direction the inequality should go. They think that the alligator wants to eat the h of x, so you end up with the alligator's mouth pointing away from this expression. The alligator wants to eat h of x. This is h of x. The alligator wants to eat that thing. Right? I don't know if you've ever drawn an alligator for the inequalities. Okay. And now I'm going to try to isolate for x. That's not a great idea. You could try solving this inequality by subtracting 32 from both sides and factoring. I'll let your advanced functions teacher show you more of that. So I'm going to try solving by isolation. I subtract 5 from both sides. That should maintain equilibrium. That leaves me with 27. I divide both sides by positive 3. No problem. Dividing both sides of an inequality by positive 3. But then, when I decide to try to solve by isolation and I take the square root of both sides, I need to consider both the positive and negative value of the argument on the left-hand side, not the number on the right-hand side, like I've been taught every single time I solve an equation. So here's hurdle number one. One, remembering to do plus minus, and two, remembering, even though this is the first time you're doing it, maybe to place it on the variable side, not on the number side. It's false if you put it on the number side. I now need to split this up into two separate cases. Either x minus 2, positive x minus 2 is greater than 3, or the opposite of x minus 2 is greater than 3. I solve each one of these as a linear inequality, and I get x is greater than 5, or let's see, I'll divide both sides by -1. When I divide both sides by -1, I reverse the direction of the inequality. Then I can solve like a linear inequality, and I get -1. Okay. So there's my conclusion. I check it for contradictions or truisms here. I get here's 5, here's -1. X is greater than 5, or x is less than -1. So my domain of H is the set of all x values such that x is less than -1, or x is greater than 5. X is an element of the real numbers. Okay. I mean, I don't know if I made it look easy, but I certainly didn't take my time here. But notice how many new things there were for us to consider. Where if you're drawing a sketch, there's not much new for you to consider. Still, this one wasn't that bad. I don't think I would be convinced that this was a bad idea yet. Let's look at example number 1, where we're asked to find the range of f of x equals, oops, that's an opposite of x times x minus 4. If, and we'll say, just to speed things up, we're working under these restrictions right here. Okay. So algebraically, what I'm going to do, instead of undoing operations to try to isolate x, I'm going to unisolate x. I'm going to build up operations. The problem is I don't see this as a list of operations on x. So now if I'd used the sketch that we had built in class, I would already know how to write this function in vertex form. I'm going to pretend I don't. I could find the roots and draw the sketch or determine the vertex form like we did in class. Let me instead do another example of completing the square, just in case you're interested in reviewing that. So I expand, and then I regret expanding everything because now I need to remove a factor of -1. That's all right. Now I will complete the square. X squared minus 4x, split those evenly. Means an addition of 4 will complete my square. -1 x squared minus 4x plus 4 is a perfect square. Have to subtract the 4 to balance that. Let's try. I'm not in a rush. I was going to try factoring and distributing on the same step. Squared minus 4, and now I'll distribute through. So, I mean, here's one disadvantage. First off, I'm not sure if you're even convinced that you would need it to be in a vertex form. But the advantage of vertex form or transformational form is that there's only one instance of x, and here I have only one instance of x. And this didn't take a short amount of time. I probably could have had this function sketched and ready to solve. And I haven't actually done anything towards solving the inequality. So here we go. And this is kind of interesting, worth seeing, but watch when things get complicated here. I'm going to change this x into the opposite, or 4 more than the opposite of the square of 2 minus x. I'm going to build these operations in a bed mass order. I'm not undoing the operations. I'm not peeling an onion. I'm wrapping the present or onion or whatever, ogre. Okay, so the first thing I'm going to do is I'm going to subtract 2. Then I'm going to square both sides. And that's going to be problematic because one side's going to be negative and the other is going to be positive. Then I'm going to multiply by -1, and that'll cause a reversal. And then I'm going to add 4. Okay. So let's try that. I want to subtract 2 from x, so I subtract 2 from the inside, from the left side, and from the right side. That maintains equilibrium. That gives me -5 less than x minus 2 less than 1. That wasn't so bad. Now I'm going to square all sides. And here's the problem. When I solve an inequality, if I multiply by a positive, I don't change the direction of the inequality. If I multiply by a negative, I do change the direction of the inequality. And squaring introduces its own natural restriction. So trust me on this, that you have to split this once again into 2 separate arms. Graphically, it's actually the 2 separate arms of the quadratic of the parabola that we're looking at. Just split it up and then square both sides here. You're squaring both sides. When you're squaring both sides here, you are multiplying by a negative. So you change the direction of your inequality. Come back to this in a second because I'm not done here. I square both sides here. I'm multiplying by a positive. I don't change the direction of my inequality. But tell me about the square of a number. The square of a number isn't just anything that's less than 1. The square of a number also has to be greater than or equal to 0. Here, the square of a number can't be any number less than 25. It also needs to be greater than or equal to 0. Here's that natural restriction that occurs. Natural restriction that occurs when you square both sides. And that's really easy to forget if you're just trying to do the algebra. I mean, it's easy to understand that the square of a real number can't be negative. Next, I'm going to multiply both sides by -1, or the inside, left side, and right side here. That'll give me -25 is less than the opposite of x minus 2 all squared is less than or equal to 0. And then I add 4 to the left side, the inside, and the right side. So this is telling me -21 is less than, is this f of x? Is less than or equal to 4. And then over here, where am I? I think I'm ready to multiply both sides by -1. X minus 2, again, forgetting that. Change the direction, and then add 4. 4 less than or equal to the opposite of the square of 2 less than x. 3. And I recognize this expression. I was building up to that expression. Okay, now I look at these 2 inequalities and I take the one that shows me, like that here, this is basically saying the right-hand side of this parabola has a maximum of 4 and a minimum of 3. But the left-hand side of this parabola has a maximum of 4 and a minimum of negative 21. Graphically, I'm trying not to sketch this because, I mean, if you're going to sketch it, you might as well solve the entire problem by sketching, right? That's what we're looking at. You've got a right-hand arm that's between 4 and negative 3, exclusive on the 3, inclusive on the 4. You've got a left-hand arm that goes all the way down to negative 21. So this function definitely reaches heights like negative 20 and negative 20.9 and negative 20.9999. So there is my range. But my goodness, that was much harder than drawing a sketch, substituting in my endpoints, and looking at my sketch to figure out where's my lowest value, where's my highest value. Do you see how the sketch makes it pretty obvious that we're going to have an inclusive case on the maximum and an exclusive case on the minimum as well? So please, please, please solve by sketching. You will have to use this in future courses. Completing the square is a skill that we don't use in the future. Solving by sketching is a skill you will use in the future. So practice that skill, please.